I just, okay. So guys, these expressions basically represent the whole statement and a conceptual understanding of what's happening to the function in general. What is this reflection? Yeah. Okay, so this is a reflection across the x-axis. Did you guys hear what she said there at the very beginning? Instead of just saying reflection across the x-axis, she used the word vertical, reflection across the x-axis. If you make a statement like that, you're going to tell yourself which variable you're impacting. So the word vertical is not necessary, but it's kind of handy because if you're doing a vertical reflect, it is vertical, like, and you're changing the y value. So if you were to kind of sneak in the word vertical right here, it would imply that you're changing the y values. Does that make sense? Okay, so when you're thinking about going across the x-axis, it's a vertical reflection across the x-axis. And then this guy was the reflection across y-axis. Right? So let's just do a quick recap. If I were just to reflect, and I had a function that looked like this. Okay, so it's not something that you would type into your guide. Okay, if I had this, like, this would be considered a piecewise function. You never see anything this complex in calculus. But if I said I wanted to reflect this across the x-axis, so if I use this notation, how many invariant points would we have? Do you remember where the invariant points would land? Brody, what do we got? Not one. Because if it's a reflection across the x-axis, like this peak would go down here. This peak would now be up here, right? And this peak would be like up here. And then it would kind of shoot off, right? So if you wanted to imagine the reflection across the x-axis, does that look like a reflection across the x-axis? Where are the invariant points? Sarah?
4 invariant points.
There's going to be 4 invariant points. It doesn't have to be a dot. So a lot of people they want it to be a dot. Anytime the function hits the x-axis, there's going to be an invariant point, because when we think about what's happening here, we're taking the opposite of the y values. It doesn't matter what the x values are. All these y values are zeros. And can I take the opposite of 0? We can't take the opposite of 0. So it doesn't have to be a fancy dot. That's going to catch some people on Thursday, is I'll be like, how many invariant points? And you're going to see dots, and you're going to be drawn into the dots. It doesn't have to be a dot. It's just wherever the function touches the x-axis. Okay? How many invariant points do we have if we reflect across the y-axis? Just the one. We just touched the y-axis once. So this is our reflection across the y-axis, and that would be 1 invariant point. So this guy had 4 invariant points. This guy had 1 invariant point. Okay? We're going to learn about a new reflection right now. So we're going to reflect across the line y equals x. So this whole lesson is inverse. And if you see the word inverse, your brain is going to have to think reflect across the line y equals x. Do you guys know where the line y equals x is? Where y is equal to the x value? What would an ordered pair be on the line y equals x? 0, 0. That's going to be on the line y equals x. What other point would be on the line y equals x? 1 and 1, 2 and 2, 3 and 3, 1.5 and 1.5, 7.8 and 7.8. -15 and -15, right? So right now, what I want you guys to do, if we're going to see the word inverse, you need to think it's a reflection across this line. And we label it. So as soon as you see the word inverse, we're going to reflect across the line y equals x. And that's right here. There's two different ways that we can write this. We can write this using this notation, or we can write it using this notation. So you know how we had like reflection across the y-axis is y is equal to f negative x, close the bracket? Well, this is the notation for inverse, and this is also the notation for inverse. Okay? What we're going to do is we're going to graph this function f of x is equal to x minus 5 squared. And let's just recap what we learned last year when we're graphing that function. Like, I know you guys can type it into your calculators, but let's just take a second and find critical features of f of x. Okay, let's find the critical features of f of x before we use our calculators to get some ordered pairs. Two critical features of f of x would be x-intercept and y-intercept, right? When I say x-intercept, what are you guys thinking? If I say x-intercept, your brain has to think y equals 0, so then 0 is equal to, now you guys know that x minus 5 all squared is just x minus 5 written twice, right? So when we're finding our x-intercept and we insert y equals 0, we set each variable factor equal to 0, and I can see x equals 5. So I don't have to do it twice, it just means we have one x-intercept, not two. Right? And remember, parabolas can have one x-intercept. So I'm just going to plot this 5 and 0. Now, if I said y-intercept, what are you guys thinking when I say y-intercept? This is x equals 0, and then this would become like y is equal to 0 plus 5 all squared, so then y ends up being 25. That's not going to be something that we're going to be able to plot on this parabola. But I could find it. Yeah? Ladies, do you want to sit in this pot over here because it's such an awkward angle? Are you okay? Yeah? Okay. Okay, now what we're going to do is we're going to type this into our calculators and we're going to get a table of values because we need to graph this accurately. Okay, so I've got my 5 and 0. Can I get you guys just to, like, on your graph, call this your f of x, and we're going to grab a table of values. So type it into your calculator. Now I've already got the 5 and 0, so let's grab a couple ordered pairs on either side of that 5 and 0. My calculator always takes so long to boot up. So you guys are probably way more efficient than I am, because I have to be super patient with my calculator. And it's just not going to open up for me. Can you guys give me a couple ordered pairs? Can you tell me, please, the x value? Like if I have an x value of 3, what's my y value? If I've got an x value of 4, what's my y value? And then 6 and 7. Can I get you guys just to give me those ordered pairs? I have no idea why this is just not opening up for me. Yeah, what do we got? 3 and what?
3 and 4.
Okay.
4 and 1.
Yeah.
6 and 1.
Yeah. Perfect. Do you guys see that we've kind of gone up on either side on the y value? So this is my vertex. When you have a parabola and you have only one x-intercept, that means that has to be your vertex. So we're just going to plot a few of these ordered pairs. So I've got my 3 and my 4. I've got my 4 and my 1. I've got my 6 and my 1. Okay, so this is what we have. And I'm going to graph my f of x. I'm going to make sure that this extends up as high as it possibly can. I want to actually kind of see where it interacts with y is equal to x. So this is my f of x. you make sure your graph extends to the ends. There's the graph of f of x. If I'm going to graph the inverse, which is the next step in this whole process, it says write the equation, sketch the graph of, this is the inverse on the grid above. So I'm going to do this one in blue. So as soon as you see this notation, I need you guys to think inverse. And so I'm going to do it in red, not blue, because I did my reflection line in blue. If I want to graph the inverse, all I want you guys to do is swap the x's and y's. So we had 3 and 4. On my inverse, it becomes 4, 3. I had 4, 1, it becomes 1, 4. I had 5, 0, it becomes 0, 5. I had 6, 1, it becomes 1, 6. I had 7, 4, it becomes 4, 7. If I want to graph the inverse, okay, so I want to graph the graph that's going to be a reflection across the line y equals x. These are my ordered pairs. Do you see that this is a reflection across that line? So when I had 3 and 4 before, it was here. This is 4 and 3. Does it look like it's a reflection across the line y equals x? Okay. My next ordered pair is 1 and 4. Does it look like it's a reflection across the y equals x line? Do you guys see that? Okay. If you were to fold it here, would these two land on top of each other? And then we've got 0 and 5. These would be reflections. And then I've got 1 and 6. And then finally I've got 4 and 7. So I'm going to graph my parabola. Now, just like when we had a reflection across the x-axis, the invariant points were on the x-axis, we have a reflection across the line y equals x. So there's invariant points on the line y equals x. And they don't have to be 4 and 4. They could be, like this guy, looks like it's like 3.2-ish. So if we're reflecting across the line y equals x, invariant points land on the line y equals x. So this is my f of x. This is my y is equal to f to the negative 1 of x. This is your inverse. And if you were to fold on that blue line, that y equals x, it would land on top of itself. So what we're going to do, so when you see the word inverse, you're going to think reflect across the line y equals x. You're going to think swap x and y. So you're going to have to swap the x and y. Okay? So I've got my original in green. I've got my inverse in red. And now if we're going to find the equation of the inverse, if f of x, I'm going to color code this back to green. If f of x was equal to x minus 5 squared, another way of writing that would be y is equal to x minus 5 squared. If you want to find the equation of the inverse, if I want to find the equation of this red line right here, you would swap the x's and y's and solve for new y. So swap x and y, and then we solve for the new y. So when you're coming up with the equation of that sideways parabola, I'm going to take my original function, I'm going to swap the x and y, and now I have to solve for the new y. How about I get the y all by itself? What's your first move? If you're going to isolate for the y, I just swapped the x and y. What's my first move? Got to get rid of squared. How do I undo square root? But guys, remember, when you apply the square root, you have to make it positive negative square root. The radical wasn't given to you as a positive. So we know that negative 3 squared gives me 9, but positive 3 squared gives me 9. So if I say x squared gives me 9, I have to acknowledge both the positive and the negative, right? You guys remember that? So whenever you apply the square root, you have to put plus minus. So now I've got plus minus the square root of x plus 5 equals y, and my inverse equation actually has a positive and a negative component to it. Oh, there we go. Okay, so how am I going to type that in? I'm going to put the original function in first. So if I've got x minus 5, close the bracket, squared, and if I want to do my inverse, I'm going to do the negative 1 first. I actually have to do it in 2 parts. And then I have to do the plus version. So that's how we have to represent the plus minus root x plus 5. And there, like you can see, it kind of comes at you in 2 components. So my inverse, so I'm just going to draw my inverse line. Y equals x. I'm going to make it dashed. Oh, and it didn't show up dashed at all. Okay, this is my line y equals x. You can see the invariant points happen on the line y equals x. You guys see that? So this was my original function. This was my inverse. How do I draw the inverse? You swap the x's and y's. Okay? How do we solve the equation of the inverse? We swap the x's and y's. We solve for the new y. Okay? The big idea, swap the x's and y's, and that's going to give you this reflection across the line y equals x. Okay? So it says mark the invariant points on the grid. I've already done that in black. Like right here, these are my invariant points, and I marked them in black. There's 2 invariant points, and I'm just going to indicate 2 invariant points on the line y equals x. So it has to be on the line y equals x for it to be an invariant point. And it doesn't have to be perfect integers. It doesn't have to be -1, -1. It could have been -1.5 and -1.5. It could have been -1.38 and -1.38. Like, it doesn't have to be a nice neat integer. Okay, so here's the big question that comes up when we're dealing with inverse. In grade 10, you had a whole unit of study called relations and functions. Okay? And in grade 10, you had to decide, is it a function or is it not a function? Is it a relation? Do you guys remember what rule or what strategy you guys used to determine if something was a function or not? So we're going to get back to that question, but I'm going to review some grade 10 with you guys. Okay, so is it a function? Okay, this is a linear function. It is a function. The rule that you guys used in grade 10 when you were determining if something was a function is you'd ask yourself, does it pass the vertical line test? Do you guys remember that phrase, vertical line test? If it passes the vertical line test, if it only hits the function once at any given point, then that means it's a function. And wherever I draw a vertical line, I'm only hitting the graph once, which means it is a function. Do you guys remember that? Okay. So last year, you guys learned about quadratic functions. We call it a quadratic function. It passes the vertical line test. Yes? Okay. Last year, you guys learned about this guy. Is it a function? It passes the vertical line test. Okay. This is called an ellipse. Is it a function? It doesn't pass the vertical line test. If I draw a vertical line and it hits it twice, it doesn't pass the vertical line test. This would be a relation, not a function. For every input, we want 1 output. We don't want to have the option of 2. Does that make sense when I say that? Okay. So if I had a parabola here, let's say this was 0 and 4, and this was -2 and 0, and I said graph the inverse, this -2 and 0 would become 0 and -2. This 0 and 4 would become 4 and 0. My inverse would look like this. So that it's not supposed to be a corner. Like, make sure, I'm going to fix that because that looks nasty. my inverse would look something like this. And you guys see that if I would have folded it on the line y equals x, it would have been the same. Like it would have landed on top of itself. Yeah? Parabola is a function. Is the inverse a function? No. It fails the vertical line test. When I put like x equals 4 in, I get two possible outputs, right? And we don't know which one would be. So this is not a function. Is it a function? No, because this actually is a vertical line right here, and there's multiple ordered pairs. So in this particular piece, it doesn't pass the vertical line test, so this is not a function. Do you guys get that? Okay. Now we're going to be about to learn the skills of polynomials. Is this a function? If I were to reflect this across the line y equals x, would it be a function? What happened with the parabolas, the parabolas kind of flipped on their sides, right? Like when you're doing your inverse, it would flip on its side. If you flip this on its side, would it be a function? No. Like if you wanted to graph a couple ordered pairs like -2 and 0, here's another critical ordered pair, let's say 1 and 4. Here's another critical ordered pair, let's call this 3 and 0. Like if you, even just the -2 and the 3 and 0, so -2 and 0 becomes 0 and -2, 3 and 0 becomes 0 and 3, right then and there, it doesn't pass the vertical line test. Do you guys see that? So the inverse would not be a function. So when we come back to this question right here, I'm going to send you guys the whiteboard shortly. It says, is the inverse a function? And so we just kind of recapped what was a function. Was the inverse a function? The answer would be no. And in grade 10, you would have called it a relation, not a function. But we're just going to say no, not a function. It does not pass the vertical line test. Okay, and when we're looking at that, we can see this guy does not pass the vertical line test. The original was a function, but this guy does not pass the vertical line test. In calculus, you're going to do something called integrals, and often you're going to want to limit your original function so that the inverse will be a function, and we're going to be diving into that right away. Guys, go to the whiteboard. Bring your calculators. When you see this notation, and so this is what you're learning today, as soon as you see the word inverse, or whenever you see this notation, your brain has to think inverse. So what you're learning today is all about inverse. Now, inverse can be written like this, or it can be written like this. That also means inverse. As soon as you see the word inverse, as soon as you think the word inverse, I want you guys to think swap x and y. And I also want you to think reflect across y equals x. Okay? So when I take a look at this, and my original function's in blue here, and I know that your guys' function is not in blue, but that's okay. So my f of x has a table of values here, and the table of values would be -4. So I've got -4, +4. I've got -3 and 1. I've got 1 and -1. And then I've got 3 and -3. If I'm going to graph the inverse, so this is my y is equal to f to the -1 of x. I'm going to color code that. We're going to swap the x's and y's. So if I want to graph this guy, -4 and 4 becomes 4 and -4. Negative 3 and 1 becomes 1 and negative 3. 1 and negative 1 becomes negative 1 and 1, and then we have negative 3, positive 3. Now from the table of values, I can't see any invariant points, but we are going to have invariant points, because notice I need to draw my reflection line, and any time I touch that reflection line, we've got an invariant point. This is my invariant point. It didn't have to happen on the table of values. It didn't have to be an integer. It could be like, right now, this looks like it's like negative, let's say negative 0, negative 0.3, I don't know, and then negative 0, I don't know what it is, I just know that it's on the line y equals x. It doesn't have to be an integer. So when I graph the inverse, I'm going to plot my 4 and my negative 4. So that point has just been reflected across that line. And then I've got 1 and negative 3. We're going to hit this invariant point. Make sure you hit the invariant point. And then I've got 1, negative 1, and 1. So I'm just going to connect these. I'm going to make sure I hit that invariant point. And then I've got my negative 3 and positive 3. Do you guys see that if I would fold on the line y equals x, it should land on top of itself? Is the inverse a function? Does that red function, it passes the vertical line test. Guys, this is a function. We're good to go. It is a function. Both the original and the inverse are functions. And then right here, I just says label the invariant point for each of the above transformations. This is my invariant point. So you guys are learning one more reflection. That's all it is. It's one more reflection, and you guys can do this. Guys, what type of reflection was this guy? You should be able to read the notation just by looking at it. So y is equal to f, negative x. Which reflection line are we going across this time? This one is a negative b value, so it's across the y-axis. Quickly draw the reflection across the y-axis. Indicate the invariant point. The invariant point will land on the y-axis. Is the inverse or is the reflection across y equals x a function? It is. The only time you're going to question whether something's a function is if you do the inverse. And then this last one, this is a reflection across the x-axis. And if I reflect across the x-axis, this is below the x-axis, it becomes above. If you wanted to deal with the mapping, you could set up your mapping. Your invariant point is going to happen on the x-axis. This is my invariant point on the x-axis. Are we okay with that? Okay. We're just going to quickly sketch y is equal to the square root of x minus 2, and then that's all we're going to do today. We'll continue task number 3 shortly. We've done a couple of radical functions. Now what I want you guys to do is to notice that this radical didn't have a plus minus in front of it. It was given to us as a positive square root function. Okay, so we don't insert a plus minus if the radical was given to us. We only apply plus minus if we had to actually apply the square root. Guys, what are the restrictions on the variable x here? Guys, don't pack up yet. The bell's not ringing. You're going to notice across the hall, often they'll pack up in a religion class, but not in a math or a bachelor class, okay? And that's always at teacher discretion. So guys, we always take our radicand to make it greater than or equal to 0. And when I isolate for x, I know that this is going to give me my domain of my radical function, and it's the restrictions on x. Why do we have restrictions on x? We can't square root negative numbers. So when I create this table of values, if I had put a 1 in here, we would have gotten an error. And the reason why is 1 minus 2 is negative 1. We can't square root negative 1. The first number we can square root is 2. Guys, what's 2 minus 2? 0. What's the square root of 0? 0. If I put a 3 here, what's 3 minus 2? Square root of 1 is 1. If I put a 4 here, we get 4 minus 2, we end up with root 2. Not a pretty number to plot. What's the next x value that I should insert if I want a nice, neat y value that goes with it? Yeah? 6. If I throw a 6 in here, 6 minus 2 gives me 4. The square root of 4 gives me 2. So that's a nice, neat graph. So all I want you guys to do before tomorrow, I want you guys just to plot. We're going to be all ready to go to dive into this example tomorrow. So this is y is equal to the square root of x minus 2. And we're going to connect this to inverse tomorrow. Okay? I will mark your quizzes probably by 4:30 today.